Hello and welcome to video 3. I just wanted to pick up from where we left off last lesson. So last lesson we sketched a whole bunch of parabolas and we also did one cubic, and we started off with the equation. So for this one it was y equals x squared plus 3x, and we used our calculator to work out the gradient of a tangent to this function anywhere along the function. So we found that the gradient function was given by y dash equals 2x plus 3, and I promised to talk more about this lesson, which I will. But we found that if we wanted to find the gradient anywhere along this function, we were able to use this formula. For example, we got our calculator to draw a tangent here at x equals minus 4, and we did that. And we found that the gradient right there could be found by substituting x equals minus 4 into this. So the gradient when x is equal to minus 4 ended up being minus 5. So that tells us that this tangent has a gradient of minus 5. We can choose any other point anywhere along this parabola. So let's say we want to know what the gradient is here at x equals 0.5. Okay, so we want to know what is the gradient of the tangent to this curve when x is equal to 0.5. Okay, so there's our tangent. That is meant to be a line that's just touching that once. So we can say when x equals 0.5, the gradient function is given by 2 times 0.5 plus 3 is equal to 4. So that tangent there has a gradient of 4. This process of getting from here to here, and we'll talk more about this later as well, but this is sometimes referred to as taking the derivative. So we are deriving a formula for the gradient of the tangent at any point along that curve, or differentiating. So they're two words that you need to become familiar with: derivative and differentiating. So that's where we were last lesson. We also did that for some other curves, and what we ended up with, well, our first example, and it's the one I've spoken about above, y equals x squared plus 3x, and our gradient function, or our derivative, ended up being 2x plus 3. For our second one, we had y equals 3x squared minus x, and our derivative function ended up being 6x minus 1. For the third one, we had y equals minus 5x squared plus 20, and our derivative function was equal to minus 10x. And the fourth one, we had y equals x cubed minus 4x, and our derivative function ended up being 3x squared plus 4. And I said to you that you can probably see a pattern. Now, if you haven't seen the pattern, I'm just going to rewrite these a tiny bit. So this first one, I'm just going to write that as x to the power of 1. This one I'm going to make x to the power of 1. This one I'm going to change to 20x to the power of 0. And I'm going to make this an x to the power of 1. Now, what I'm hoping you have seen is that the power almost gets multiplied out the front, and then it gets reduced by 1. Okay, so we bring this down the front, 2x, and then this goes to a power of 1. When we multiply this out the front, 1 times 3 is 3, and then we're left with an x to the power of 0, which we don't bother writing in. For this one here, 2 times 3 is 6, and then a power, we take away the power of 1 from 2, we get 1. We don't bother writing that, of course. And I'll times this by minus 1 out the front, and I get x to the power of 0. Again, I don't bother writing that because it's equal to 1. Here, 2 times minus 5 gives us this minus 10, and then it's x to the power of 1. And this one disappears altogether. So we don't make it x to the minus 1. We just know that when there's a number there by itself, when you take the gradient function, it just disappears altogether. And similarly here, we times this out the front by 3. The power reduces by 1. They become 2. And this one just becomes a 4 because it's like having 4x to the power of 0. So we can see what's happening here. We haven't proven that it works. We think that it works. It's worked for all 4 of these. So I'm going to tell you that this pattern does work for our polynomials, and we could just practice a few. So I'll give you some nice easy ones to start off with. I'm going to start with, let's call this one number 5. If I have y equals x squared, what do you think y dash will be equal to? Good, 2x. In fact, I might write a few here and let you have time to have a think about them. Let's do 7. Let's make that y equals 2x cubed. And then let's try something a bit different. Y equals 5x cubed minus 3x squared plus 2x. So pause now and have a try. Did you get y dash is equal to 3x squared? That y is equal to 6x squared? And that y is equal to 15x squared minus 6x plus 2. We'll be doing lots and lots of this over the next year and a half, and we'll have lots of time to practice. So it looks like if we have y equals an x to the power of n, that we can find the gradient function by just multiplying out the front by n, x, n minus 1. So this is what we're proposing is true, and I'm telling you, you are right, it is true, and we're going to prove it in our next lesson. But we're just going to practice using it. Now, before we practice using it, this is where I want to talk to you about notation. So I have used the notation that if we have y equals x squared plus 3x, then y dash will be equal to 2x plus 3. That could also have been written, the question could have been written as y equals x squared plus 3x. We just know that as a function on the number plane, that's a parabola. And we could have written dy by dx is equal to 2x plus 3. So notice that the answer is exactly the same. The notation is different. Now this won't make much sense to us just yet, but we're getting close to the point where that is going to start making more sense to you. I just want you to be familiar with that notation. The last piece of notation we often see is to call that function x squared plus 3x. So instead of calling it y equals, I call it f of x. And we saw f of x early on last semester, but we probably haven't used it for quite some time. So for the derivative of that, we say f dash of x is equal to 2x plus 3. So all of those are exactly the same thing, just depends which textbook you're using and how they ask the question. So just be familiar with all of those. All right, this lesson's nearly finished, but I thought you might just like a few more to practice with. So let's put some more questions down here. What are we up to? We're up to question 9. 9 as being y equals x squared minus 4x, and I'll get you to write what dy dx is equal to. Question 10, y equals 3x squared plus 9x, and could you write what y dash is equal to? For question 11, I'm going to tell you that f of x is equal to minus x squared minus 3x, and get you to tell me what f dash of x is equal to. For question 12, I'm going to give you y equals 2x plus 9, and tell me what y dash is equal to. And for 13, let's go for f of x is equal to minus x cubed plus 7x minus 9. And we'll have f dash of x. I'm going to add one more because I haven't done anything higher than a power of 3, I don't think. But this just keeps going. So if I was to give you y is equal to 2x to the power of 6 minus 3x to the power of 5 plus 4x to the power of 4 minus 3x cubed plus 2x plus 99. Can you tell me what dy dx would be? So pause the video, have a go at those last ones, and I will come back with the answers. Okay, here's the answers. When we differentiate this, we get 2x minus 4. We do this one, we get 6x plus 9. This one becomes minus 2x minus 3. This one is 2. This one is minus 3x squared plus 7. And our final one is 12x to the power of 5 minus 15x to the power of 4 plus 16x minus 9x squared to be a 3 plus 16x cubed minus 9x squared plus 2. And that's it. So we've seen a little bit about the notation. We've remembered what we are doing when we are differentiating or taking the derivative. It's all in the aim of finding the gradient of the tangent at a particular point on a curve. I look forward to seeing you in video 4, where we will do a bit of a proof to show that this is true. I shall see you there. Bye.